Pizza, pizza, pie, pizza, 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 pie. Everybody's eating lots of pizza pies. Okay, so what we're going to talk about here is how if we have a changing amount of flux through a surface, it's actually going to generate an E field, an electric field. And this is where we kind of get this idea of electromagnetism, and even better yet, well, from that light. Now, it's not something we're going to spend a lot of time talking about, but if we have that wire, you know, we have a wire here, and there's an electric field, or there's a electron in it, right? So there's like electrons in here. We know that an electric field is given by the equation a force per unit charge. So if whenever we created these EMFs inside of it, you know, we had the negative side and the positive side because it split. If we had a force that caused this to happen, well, it's happening per unit charge here. And that means an electric field is being created, which is kind of wild. And if we kind of take a look at this, what we'd actually see about this is we know this force is Q V cross B. Let's pretend the sign is 90. And then if we divide this by Q, we actually see the electric field here is just equal to a velocity multiplied by a B field, or rather crossed with a B field. So we could actually just say that the electric field is equal to V cross B. So if you have a particle moving with some velocity through a B field, it's going to create an E field, which is kind of a weird idea. That's not something like super intuitive there. If we actually wanted to go and pull one of Maxwell's equations out, it's actually Ampere's law we're going to say here. We've already talked about Ampere's law, which is the closed surface integral, or the closed boundary integral, excuse me, of a B field along some path, so dot product of some path. We said that this equals mu naught times the current that's enclosed here, but this isn't a full statement. If you actually go a little bit further, you'll actually see that you have to add a term to this, and we're not going to in this class. In this class, or rather the AP Physics C course, that's where we end. But if you wanted to be complete here, there's technically another term here, which is mu naught epsilon naught, permeability of free space for both magnetic fields, oh, I can't speak this morning, or electric fields, and then it's multiplied by a changing electric field with some amount of time here. So we see that a magnetic field is going to create a changing electric field. And what else is really cool is that if we take this same idea for Faraday's law of induction, which we've been talking about, and we use it, we can say that the closed boundary of an electric field, well, that last E is kind of weird looking, dotted with ds, that's going to equal the negative change in magnetic flux in an amount of time. So that's if you walk around the surface of a boundary of an electric field, which is not exactly what we've talked about with what we've done here. But yeah, it's a kind of neat thing that's going on there. Basically, as we create one, we create the other. So we can just keep making change in B and E fields. So it's kind of a weird thing, but that's generally speaking how we get light. So that's what we're going to talk about for this. As you'll see later on, we'll come back to this idea a little bit. But for right now, this is finished. Adios, and y'all take it easy. Pew.